La siguiente presentación estará a cargo de Christopher Tumey de FL Smith, quien nos hablará sobre innovaciones en el diseño de los pisos y la operación en los silos de almacenaje.
Sí. Gracias. Okay, hello everyone. Good afternoon. Thank you very much for attending this presentation. My name is Chris Toomey. I work for FL Smith. I work in their pneumatic transport department. So I focus on pneumatic conveying, but also on silo blending and extraction systems for the cement industry. The title of my presentation is Innovations in Storage Silo Floor Design and Operation. Basically, my presentation is a story about a cement plant, as you might imagine. This particular plant is located in British Columbia in Western Canada. And in 2005, this plant needed to find a new storage for both cement and fly ash. And this is the story of why they needed new storage, how they made the decision of which silo technology to use, and then finally, what are the results? How are the silos working today? First, I'd like to give you a little bit of background information. This will help you understand the situation that the plant was in. This plant was constructed back in 1956, and it had originally an old wet kiln line. About 10 years later, they added a second wet kiln line. But in the mid-1990s, they wanted to modernize the plant, and that modernization was commissioned in 1999. The new plant had a new dry pyro line with a 5-stage precalciner, 40,000 tons of clinker storage, a new 3,000 ton per day cement mill, and a new 7,500 ton cement storage silo. The design capacity of the new plant was 1 million tons per year of cement. But through optimization during the first weeks and months of operation, they were actually able to achieve about 15% more than that, or 1,150,000 tons per year of cement. And actually, they could even exceed that value by a little bit. So that's one of the reasons why in 2005, the plant had a task. They had to find new storage for cement and fly ash. And whatever solution they came up with, it needed to meet two broad objectives. The first broad objective was to meet the design constraints of the plant and the project, and I'll talk about those design constraints. But it also needed to promote their corporate sustainability initiatives, or in other words, it needed to be a green solution. First, I'll talk about some of the cement silo design constraints. The cement silo, first of all, it needed to hold 10,000 tons of cement. There were two reasons for this. First, they needed to accommodate that additional production capacity. Second, the company had acquired some larger barges for cement transport, and they wanted to be able to load those barges very quickly and continuously in one shot. The cement silo also needed to have flexible discharge capability. So they needed to load bulk trucks to distribute cement to the local market. They needed to load rail cars to distribute cement to the United States. They also needed to load barges to distribute cement to the United States. The fly ash silo had some similar design constraints. First of all, the fly ash silo needed to be 4,000 tons of storage. They had a small fly ash silo prior to this, but there was increased demand from the local concrete market for fly ash. So this company wanted to be able to accommodate that demand and sell fly ash to those local customers. And the fly ash silo also needed to have the ability to load bulk trucks to distribute it to their customers. Some additional silo design constraints. First, the silos needed to have a low height to diameter ratio, or they needed to be short and wide. And the reason for that is because there were very poor soil conditions at the plant. This plant was built on river delta deposits, so it was very poor soil to construct large, heavy structures on. The silos needed to have a common foundation because there was limited space at the plant. And both silos needed to have complete extraction capability or complete clean out. And that's to avoid cement contamination. So when this plant emptied the silos, they wanted the silos to be completely empty or as close to completely as possible. Okay, so I talked about the basic guidelines of the project. As I mentioned before, they also needed to promote their corporate sustainability initiatives, which included minimizing carbon dioxide emissions and also improving efficiencies. So they wanted whatever solution they came up with to obviously minimize energy consumption and also improve logistics or minimize truck traffic at the plant, because they didn't want a lot of trucks just sitting around, idling, wasting fuel and wasting time and wasting money. Okay, so that's the background of what decision they needed to make. The plant then evaluated 3 different alternative silo designs. The first one they looked at was a conventional 60-degree cone silo. The second one was a central inverted cone silo. And the third one was a fully fluidized random flow silo. So if we look at a conventional 60-degree cone silo, it's a very good silo design. It's very common. It gives you very good extraction of material because you have a very steep cone angle. But you do have a lot of wasted space at the bottom of the silo. So all of this space is volume where you cannot store material. So the problem is to get the required capacity, you need to build the silo taller. And that was unacceptable for this particular project because of the civil engineering considerations at the site. A central inverted cone silo fixes the one problem because it allows more cement to be placed lower to the ground, but you still have a loss, you still have a loss of volume in the cone here, so you still need the silo to be taller than necessary. And it's also a lot of times very expensive to construct the silo and construct the cone. So the third option they looked at was a random flow silo design. And this kind of has the advantages of the other 2 designs without the disadvantages. So with the random flow silo design, there is a very small aeration area, which means very low energy consumption, a smaller vent requirement because you're not putting as much air into the silo, and also you get a less fluid and more dense discharge of material so that you can fill trucks and rail cars faster and you can fill them to a higher level more quickly. The other advantage of this type of silo is you get maximum storage with a lower height, okay? Because all of the material sits down low to the ground. There's no 60-degree cone, and there's no large concrete inverted cone to use up usable space. And by the way, that is the silo design that the customer eventually chose for this project. So we'll talk about the results of that in a few minutes. The basic design of this silo is there are 6 pie-shaped regions within the silo. And each one of these regions has small aeration zones, and it has a gathering slide to direct material to a central discharge point. The great thing, because these aeration zones are small, for this particular project, the customer required an 18.5 kilowatt aeration blower, and a 5.5 kilowatt discharge blower, so two small blowers, low power consumption. Because there is random aeration, these various zones aerate randomly, you get a little bit of blending of the material as it discharges. So you also, the plant was able to give their customers a more uniform product. And then when we compare this type of design to a standard old flat bottom storage silo, it uses about 1/10 of the energy consumption. This is a 3D model of what the inside of the silo looks like. And you can see the various aeration zones, the gathering slides. You can see it's a small steel cone with a small vent pipe rather than a large concrete cone. And you also have a very compact discharge here without the need for a very large bin or a very large dust collector, because there's not a lot of air that needs to be vented. This is a screenshot of the control system for the cement silo, and you can see these areas in green are the areas that are aerated at one time. So you can see we're only aerating a very small portion of the silo, and then there's two gathering slides aerated to direct material to the discharge point. So because you're aerating a very small amount of the silo, it's very low energy consumption. And then here's a similar screenshot for the fly ash silo. With the design is a little bit different, but you can see the same similar zones aerated at one time. So the result of the project, this is the plant, and you can see the two new silos, the cement silo, which the plant designates Silo D, and the fly ash silo, which the plant designates Silo E. So was this project successful? Well, it uses 1/10 of the energy consumption of a standard flat bottom design. Because the discharge of material was more dense, they were able to load up to 40% more material in each truck, which means they could send material out to customers faster with less pollution and less traffic. There was less air to filter, which added to the overall energy reduction. Because there was a little bit of blending of material as it discharged, there was better product uniformity. They could send a more uniform product to their customers. And then finally, they were able to achieve almost 100% extraction of the material. And this is actually a picture of the cement silo after 5 years of operation and after completely emptying the silo. You could see this is a 10,000-ton silo, and there's very little material left over in the silo. So this is well over 99% extraction of material, which is exactly what the customer wanted. So was the project successful? It was definitely successful, and the plant has lower operating costs and a cleaner environment because of it. That's all I had. Thank you very much for your attention. And once again, my name is Chris Toomey. If you'd like if you have any questions and would like to speak afterwards.
Gracias, Chris.